Right, so today we're going to look at the link between what we've done on intermolecular forces and forces between particles and enthalpy, or the total energy in a substance, which includes kinetic energy and bonding energy. So the first thing we're going to look at is a thing called enthalpy of fusion. And basically what that is, it's the amount of energy required to turn 1 mole of a substance from solid state to liquid state at its melting point. So we're not worrying about the amount of energy required to lift it up to the melting point. We've already got to the melting point. So for water it would be 0 degrees Celsius, for example. So you're not using any energy there. So in other words, it's the amount of energy required to break enough forces between all of the particles to turn it from solid state to liquid state. Okay? So in water, that means breaking enough of those hydrogen bonds so that the water goes from ice to fluid. Okay? So the key things to remember if you're going through the definition are basically that you are looking at 1 mole. It's energy added, so it's going to be endothermic. So it's going to be a positive value. Okay? It is already at the melting point. So we're not counting the energy taken to get to that point. So these are the key things to remember about it. And of course, if it's melting point, it's from solid state to liquid state. We use these values to give us an indication of what type of forces are between the molecules or between the particles if it's, say, ionic. If this value is very, very high, that indicates that the forces are quite strong. Okay, so a high value equates to strong forces or bonds. Conversely, a low value means that it's going to have weak bonds. So what do I mean by strong and weak? Well, your value for something like salt, for example, which is ionic, would be extremely high. Be an extremely high value, so that would be ionic because they are very, very strong bonds. Of course, something like diamond, which is a covalent network, same thing. It'll be a very, very high value. Even once you get up to, actually, for this case, that was a bad example because in diamond it atomizes, so it turns, it skips the liquid and the gas phase and goes straight to atoms. So basically plasma. So that's what I mean by strong. Sort of a middle range one, you're going to see a lot of those, and it's where you're comparing ones. So if it's a higher one, it suggests that it's got higher values. That's going to be things like water, where it's got hydrogen bonds between the particles, because hydrogen bonds are relatively strong. Whereas, say, for example, carbon dioxide, again, one that sublimes, but let's say we could make it a liquid, that would be very low because it's non-polar and quite a small molecule. So the temporary dipole forces are very weak there. Bromine's a good example, actually. Non-polar because it's an element, so it's non-polar. It's a liquid at room temperature because it's got a large enough electron cloud to have enough temporary dipole forces for that, so it's not a gas. But if we take it down to its melting point, then it doesn't take much energy to go from solid to liquid because they're only temporary dipole forces. All right. So that's how we use these values, and you'll be asked to compare different values for different molecules to infer the types of bonding within those. Okay. The other one that we have to know is our enthalpy of vaporisation, and same sort of thing applies. Again, it's looking at the amount of energy for 1 mole. Okay, it's the amount of energy required, so it's endothermic. And it's turning that 1 mole from the liquid phase to the gas phase, so that would be at its boiling point. So we've already raised it to the boiling point. Now you'll find that enthalpy of vaporisation is always a larger number than enthalpy of, sorry, I should write it on right. You always find it's a very large value, just need to double check. Enthalpy of fusion, you're having to break enough bonds for it to be fluid. Enthalpy of vaporisation, you're having to overcome all of those bonds so it can become a gas. So there's basically no forces between them. So I'm pretty sure I'm right in saying you'll find these values should be higher than the fusion ones. They should be higher because you actually have to break the last of the bonds. In enthalpy of fusion, you actually only have to break a few of them. It's more about weakening them so that the particles can move. In this, you have to break them. They have to be gone. So in liquid water, there are still hydrogen bonds there. But in steam, there's no hydrogen bonds there. In liquid water, there's still quite a lot of permanent dipole forces. In steam, there are none. So these values are going to be higher because it's having to break the last of those bonds. Again though, it can be used to do the same comparison, so this will be used in the same way. A high enthalpy of vaporisation suggests that there's a lot or strong bonds there, and a low value means that there's very few bonds or they're very weak. So again, we can use this. So there's only two simple ideas, but actually they can give you more evidence as to what a substance is made up of. Is it a non-polar molecule? Is it a polar molecule? Is it a polar molecule with hydrogen bonding? Is it a non-polar molecule with hydrogen bonding? Which, by the way, can exist if it's big enough. Think of things like octanol, doesn't dissolve in water, but can do hydrogen bonding, so should be able to. Well, that's just because it's non-polar, that the whole molecule can't be surrounded by water. As we get higher, is it metallic or covalent compound network, or is it ionic? Those ones have got very strong bonding, so harder to turn into a gas. Alright, so both of these ideas, enthalpy of fusion, enthalpy of vaporisation, are used to help give you more evidence to determine the bonding within a substance, what type it is. Alright, stop there.